this video, we're going to start the conversation about section 6.5, logistic growth. But before we do that, let's review integration of using our technique of partial fractions, because we're going to need this eventually to solve the logistic growth differential equation. So in our integral, 3x to the fourth plus 1 over x squared minus 1, we see the degree of the numerator is greater than the degree of the denominator. So first we're going to have to long divide. So I'm going to leave some space there. We say what times x squared is 3x to the fourth, and that's going to be 3x squared. 3x squared times x squared is 3x to the fourth. 3x squared times a negative 1 is a negative 3x squared. We're going to subtract, so we get rid of the x to the fourth, but we get 0 minus negative makes it a 3x squared plus 1. And we do it again. This time we say plus 3. So 3 times x squared is 3x squared. 3 times negative 1 is negative 3. We remember we're subtracting. The x squareds drop out. 1 minus negative 3 is 4. So we're going to get our remainder over what we divided by. So our integral has now become the integral of 3x squared plus 3 plus, and then I'm going to make a separate integral here for the 4 over x squared plus minus 1, which we are going to factor into x minus 1, x plus 1. So the first part, the integral of 3x squared, is going to be just x cubed plus 3x. But the more interesting part is we're going to think of this as being a over x minus 1 plus b over x plus 1. If you recall, we're going to multiply by that common denominator, so we will get 4 on the left side equals, and then we'll get an a times x plus 1 plus b times x minus 1. This has to be true for all values of x, so in particular, if we choose x to be equal to 1, we'll get 4 is going to be 2a, and then the b's will drop out, so that's going to tell us that a is 2. If we choose a to be negative 1, we'll get 4 is equal to a negative 2b, so that means that b is going to be negative 2. So our second, I'm going to come way over here, our second integral has now become a over 2x minus 1, and then we're going to get, shall I call it a minus 2 over 1 over x plus 1. And so the first integral is going to be 2 natural log of x minus 1 minus 2 natural log of x plus 1. Now, there's going to be, as we'll see when we go to actually evaluate this many times, looking ahead into the future here a bit, this is where, using our property of logarithms is actually going to be really important. So in this particular example, it wouldn't really matter, but I just want to kind of jog your memory and just get you used to looking for this. So we can bring these into exponents and call that the natural log of x minus 1 squared. Don't really need the absolute value anymore because the squaring is going to guarantee that's going to stay positive. Minus the natural log, and same story here, we can call that x plus 1 squared. And then remember, because of the minus, we can condense this into a single logarithm, x minus 1 squared over x plus 1 squared. So there's our logarithm. So bringing in that other piece, our final answer is going to be x cubed plus 3x. We're going to say plus this natural log of x minus 1 squared over x plus 1 squared. and then plus our constant of integration. So a lot going on there. So I'm going to slide this up a little bit. So we're going to talk now about what's known as the logistic growth differential equation. So the motivation behind this is we saw earlier that a lot of exponential growth is modeled with our differential equation, that the rate of change is proportional to the amount present, the current population. And that leads to exponential growth models. We saw that this is going to lead to, let me use a population. So we'll say P of T is going to be some initial amount, P sub 0, e to the kt. But in reality, population growth cannot grow exponentially forever. Whether that's human population or bacteria population or antelope population, eventually they're going to kind of eat themselves out of house and home. And so there's going to be a largest population that is sustainable. So a more accurate model of population growth is what's known as the logistic growth model. And that's given by this dp dt, the rate of change, is proportional to the product of P and capital M minus P, where M is known as the carrying capacity. And that turns out to be the maximum sustainable population. And so when you graph this, you can see over here on the left, you get that there's going to be a horizontal asymptote at P equal to M, that carrying capacity, and then another horizontal asymptote to the left that is 0. And then it's going to look like that kind of stretched out S. So the idea is it grows exponentially initially. It takes off quickly, but then it's going to hit an inflection point, and then it's going to continue to increase, but slowly, more slowly, and approach that carrying capacity as an asymptote. So we're going to ask some questions and answer some questions about this to get a better understanding of what it is really telling us, both the differential equation and what that graph has, what the significance of it is. So the first question is, for what value of P will dp dt approach 0? So when you look at that differential equation, you can see that the values of P that will make that 0 are going to be P equals 0 when the population is 0, and also when P is equal to M. So what that's telling us is that it's going to approach these populations asymptotically. That is, as we have those horizontal asymptotes at P equals 0 and P equals M. And so that's where the population is going to stop growing. It's going to approach 0, where it'll just hit a steady state. So number 2, y equals k times p times m minus p is a parabola that opens down. And that's exactly our differential equation, where we're calling it y instead of the dp dt. So that p times m minus p is going to give us a negative p squared. So it's a parabola that opens down, and the question then is, what is the value of p at the vertex? And what does that mean? Well, we can see that if we have kp times m minus p, that it's going to be 0 at p equals 0, and it's also going to be 0 at p equals m. And then it's going to be this parabola that opens down. So we can see that halfway in between the 0 and the m is going to be our vertex. And so that means that our parabola that opens down will have its largest value at p equal to m over 2, the halfway point. Now, for us, that means that since this is our differential equation, the rate of change, the dp dt, the rate of change of the population, will be its largest, its fastest. It's going to grow the fastest at m over 2. And remember, that means in terms of our derivatives, that is, that's going to make this be an inflection point. So the maximum value in a growth in a derivative graph corresponds to an inflection point in the original function. That's when that population growth is going to be its steepest, its fastest. And so that kind of gets to number 3. Why is the growth rate maximized when the population reaches half of the carrying capacity? And that's exactly because of the fact that our differential equation is a parabola that opens down, and the vertex of that parabola is at m/2. Now, if the initial population is less than m, is the initial growth rate going to be positive or negative? So if we imagine that you jump into this graph and you start somewhere that is below the carrying capacity, then you can see that our growth rate is going to be positive. It's going to be increasing there. Our population is going to be increasing. So our dp dt is going to be positive. You can also see it in the graph of this parabola, because this is our dp dt right here. And so if you do an initial population that's less than m, that's going to put you at an x value or a t value somewhere in here, and that's going to give you a place on that curve that's positive. If the initial population number 5 is greater than m, is the growth rate positive or negative? So you can see in our graph of dp dt, if you were to start with a value that is bigger than m, that would put you on a part of the parabola that's below the x-axis there. That's going to be a negative value. So our growth rate is going to be negative if we have an initial population that is bigger than the carrying capacity. Now what that means in terms of our growth up here is if we somehow start with a population that's more than the carrying capacity, it's going to have to decrease. Okay, so you can also see it here in our differential equation. If p is bigger than m, then that m minus p is going to be negative, and this p would be positive, which is going to make our dp dt negative, which means it's going to be decreasing. The idea being that no matter what your initial population is, it's going to get pushed over time towards that carrying capacity. If you start below the carrying capacity, it's going to want to grow up until it reaches that carrying capacity. If you somehow start above the carrying capacity, the conditions are going to push it so that you go down towards that carrying capacity, that population will decrease until it approaches that, until it gets to be that carrying capacity. If the initial population is equal to m, what is the growth rate? Well, we can see in our differential equation, if p is equal to m, then this m minus p portion will be 0, and 0 times anything is 0, which would make that dp dt be equal to 0. We can also see it on our graph. If we started right there on that asymptote, then it's going to want to stay right where it is. So if the initial population to answer the question, the dp dt would be equal to 0. It doesn't want to grow, nor does it want to shrink. So what's the limit as t goes to infinity of the population? Well, it's going to be m no matter where it starts. So it will equal m. So if it starts below the carrying capacity, the conditions are going to push it so that it tries to grow and reach that carrying capacity. If it starts above, the conditions are going to make the growth rate decrease, and it's going to push it down towards the carrying capacity. And if it starts right on the carrying capacity, it's going to have a growth rate of 0. It's going to want to stay right where it is. So no matter what, the limit as t goes to infinity of p of t is equal to m. I guess the only exception would be if the initial population was 0. In that case, it would just stay 0. All right, let's look at the next panel. So here we have an example, and these are the kind of questions that typically come up on AP questions regarding logistic growth. So it's that we're told that the growth of a population of bears, the population P of bears in a newly established wildlife preserve is modeled by dp dt is equal to 0.008 p times 100 minus p. T is measured in years. So this is our logistic growth model. So these are the typical questions you'll be asked. What is the carrying capacity? Now in general, and they like to try to disguise this a lot of times on AP questions, but whatever this second parentheses is, and it may not always be quite as clear as this, but the value of P that makes that equal to 0 is our carrying capacity. So that M is going to be 100 bears in this case. What is the bear population when the population is growing its fastest? That's always going to be at half of the carrying capacity. And so in our case, that's going to be when the population of the bears reaches 50. It will be growing its fastest. And what is the rate of change of the population when it is growing the fastest? Well, now we're going to have to plug that in. So our dp dt is going to be 0.008 times, we said 50, when the bear population is 50 is when it's growing its fastest, times 100 minus 50 is another 50. So we're getting 0.008 times 2500. So let's see, that's going to be, if I move the decimal over 3 times and back, that's going to be 8 times 2.5. 8 quarters is 200. And so because of the decimal, that's going to be 20. So it will be growing its fastest when the population is 50, and its growth rate will be 20 bears per year at that time. Very good. I'm going to do a second video where I'm going to actually solve a logistic growth differential equation. That's pretty long and involved, so I'll just make a separate video for that one.